All right. All right, ladies and gentlemen, I'm going to do a couple problems out of section 6.2. I ran out of time in class. This will be applying the normal distribution to application problems. I'm going to do problem number 10 in our textbook first. It says the average commute to work is 25 minutes, according to the 2005 American Community Survey. If we assume that commuting times are normally distributed and the standard deviation is 6.1 minutes, what is the probability that a randomly selected commuter spends more than 30 minutes commuting one way and then less than 18 minutes? So for problem number 10, they tell us that the mean of this normal distribution is 25 minutes. And the standard deviation they indicate is 6.1 minutes. And they want us to find the probability that a randomly selected commuter spends more than 30 minutes commuting one way. So we want the probability that X represents the minutes that a randomly selected commuter commutes. We want the probability that this time is greater than 30 minutes. And to do this problem, we're going to use our normal CDF function. To graph this probability as an area underneath the normal distribution curve. Remember, the mean of this distribution is 25. 30 would be up here. So we're really being asked to find this area in the upper tail of this normal distribution. And so to do that, we would use our normal CDF function. And the lower endpoint would be 30. The upper endpoint would be positive infinity, which we use 10 to the 99th power. The mean of the distribution is 25, and the standard deviation is 6.1. Getting out our calculator and dialing this up. I get a probability which is about 0.206, so about a 20.6% chance. The next part of this question, they want to know what is the probability that a randomly selected commuter commutes less than 18 minutes. This is part A. Part B is going to be this probability. The probability X is less than 18 minutes. And diagrammatically speaking, that is going to be this area underneath this normal distribution curve. 18 will be about down here. And so we're really finding this lower tail area, which is this probability. Now the lower limit is going to be negative infinity, which is going to be negative 10 to the 99th power. So again, using the normal CDF function, lower limit is negative 10 to the 99th power. Upper limit is 18. The mean is 25, and the standard deviation is 6.1. Dialing this up on our calculator using our normal CDF function. I get a probability which is about 0.126. About a 12.6% chance that a randomly selected commuter will commute less than 18 minutes. All right, that's number 10. For number 18, Americans spend an average of 7 hours a day looking at a screen. Assume the variable is approximately normally distributed and the standard deviation is 1.3. Find the time limits for the middle 50% of screen viewers. Okay, so for number 18, they indicate that the mean is 7 hours and the standard deviation for this normal distribution or these normally distributed times is 1.3 hours. They want us to find the middle, the limits for the middle 50% screen viewers. So what we're interested in finding here for this normal distribution is the z-score, or excuse me, the times x sub 1 and x sub 2, in between of which lies 50% of the area of the curve. 0.50 is this area in the middle here. All right, now to find these values, we're going to have to use our inverse norm function. And remember, the inverse norm function always needs to have areas to the left of a value we need to find on the horizontal axis. So I need to have this area down here. Well, the middle area is 50%, and the area underneath the whole curve is 100%. So 100 minus 50% would leave me with 50% allocated equally to the lower and the upper tail. So 50% divided by 2 would leave 25% of the area in the lower tail. So inverse norm, the area to the left of this x value we wish to find is 0.25. The mean is 7 and the standard deviation is 1.3. Okay, so we will bring up our calculator and we will find that value using the inverse norm function, which hangs out in your distribution mode. Again, the area is 0.25. The mean is 7 and the standard deviation is 1.3. And this would be equal to about 6.1. So this would be equal to 6.1 hours. And remember, the mean was 7, okay? So by symmetry, if this is 6.1 hours, 7 minus 6 is 1, and this is going to be like around 8 hours. You want to be more exact in finding x sub 2, you would have the area below x sub 2 as being 50% plus 25% or 75%. So you use the inverse norm function and type in the area to the left of x sub 2, which is 0.75. And we can find that value exactly here. So that gives you about 7.9 hours. So this is more accurately about 7.9 hours. Okay. So about 50% of Americans view between about 6.1 hours and 7.9 hours of screen time. And that is problem number 18. All right, I'd like to do a problem like number 20 now. The weight of adult male Florida manatees is normally distributed with a mean weight of 450 kilograms with a standard deviation of 45.3 kilograms. U.S. Fish and Wildlife Service wildlife research permit allowed for the capture and release to measure 120 adult manatees in the Crystal River. How many of these adult manatees would have a weight over 500 kilograms? So for problem number 20, they indicate that we have a normal distribution with these weights with a mean weight of 450 kilograms. So with a mean weight of 450 kilograms and a standard deviation weight of 45.3 kilograms. Now, the U.S. Fish and Wildlife Service allowed for the capture and release to measure 120 adult manatees in the Crystal River. How many of these 120 adult manatees would have a weight over 500 kilograms? So we want to find the probability, which is really the proportion that would have a weight that exceeds 500 kilograms. So we really want to compute this probability here. Geometrically speaking, this probability is going to be this upper tail area here, because the mean is right here, which is 450 kilograms. So we would use our normal CDF function, where the lower limit of this interval is 500, and the upper limit is positive infinity, 10 to the 99th power. The mean of this distribution is 450 kilograms. Standard deviation is 45.3 kilograms. All right, taking this to our calculator, using our normal CDF function, let's find out what this probability or this proportion would be. Five, 3. So this probability or proportion would be about 0.135. And they want to know, of the 120 manatees that were captured and released, how many of them would have a weight that exceeds 500 kilograms. You would therefore take 0.135 and multiply it by 120. And therefore, of these 120 manatees that were captured and released, we would expect about 13.5% of them, or about 16 of the manatees, to have a weight that exceeds 500 kilograms. And that would be your answer. About 16 of the 120 manatees weights would exceed 500 kilograms. And that's one like number 20 there. All right, I want to do one like number 27 now. The average length of a hospital stay for all diagnoses is 4.8 days. If we assume that the length of hospital stays are normally distributed with a variance of 2.1, then 10% of the hospital stays are longer than how many days? 30% of the stays are less than how many days? All right. So for 27, the mean of this normal distribution, or the mean of these days or times of stay, is 4.8 days. And the standard deviation is the square root of the variance, the square root of 2.1. And the square root of 2.1 is going to be about 1.45 days. Now, what they're asking for is $10 of the hospital stays are longer than how many days? 10% of the hospital stays are longer than how many days? So here's your normal distribution of the days of stay for any hospital visit, the mean of which is 4.8 days. 10%, the upper 10% of the stays exceed how many days? We'll call this area in the upper tail 10%, 0.10. We want to find this value of x here. Since we're trying to find a value on the horizontal axis and not a probability, we use the inverse norm function. So inverse norm of the area to the left of X, and this area to the left of X is going to be 100% minus 10%, which is 90%. So this area here, down here, is 90%. So inverse norm, 0.90. The mean is 4.8, and the standard deviation is 1.45. Let's bring that up on our calculator here. So the area, again, is 0.90. The mean is 4.8. And the standard deviation is 1.45. So this is about equal to about 6.7 days. So, ladies and gentlemen, we would call 6.7 days the length of a stay after a diagnosis. We would call that the 90th percentile of all stays. That's called the 90th percentile because 90% of the stays are less than 6.7 days. 10% are greater than 6.7 days. Second part of this question wants to know 30% of stays are less than how many days? 30% of stays are less than how many days? Well, 30% of stays is less than 50% of the stays. So 30% is going to have to be an area down here. We'll call this 0.30. We need to find this X value. So to find that, we use our inverse norm function again. The area to the left of the X value we seek is 0.30. The mean is 4.8. And the standard deviation is 1.45. Oops, I got a little cut off there. So this is 0.30, comma 4.8, comma 1.45. All right, let's bring that up on our calculator. 0.30. This is about 4.0 days. Okay. So we would call this 4 days here. So 4 days is called the 30th percentile of all hospital stays after diagnosis. 30th percentile. In the sense that 30% of the stays are less than 4 days, and 70% of the stays are greater than 4 days. All right, those are the problems that I wanted to do, and hopefully now you know how to better apply the normal distribution to application problems to either find probabilities or to compute actual values on the x-axis.